A box with a square base and open top must have a volume of 32,000 cubic centimeters. Find the dimensions of the box that minimize the amount of material used. Step 1 in an optimization problem is to read it. Perhaps read it twice. A box with a square base and an open top must have a volume specified. Find the dimensions that minimize material. So we're going to draw it as our next step. We've got a box that is a three-dimensional object. It's got an open top. We know that it has a square base. So we have something like this. Since it has a square base, I'm going to call this B and B for base, and then H for height. Height could be different from the base. The volume is a constraint of the problem. That's what we call a secondary equation. So we know that the H times B squared volume has to equal 32,000 cubic centimeters. Find the dimensions of the box that minimize the amount of material used. Since we're trying to minimize the amount of material used, that is our primary equation. We need an equation for material used. Material used is surface area in this problem. So we've got surface area. I'm going to leave a little bit of space here underneath my secondary equation. Surface area is equal to, we've got one bottom, B squared. We've got 4 sides, BH. 1, 2, 3, 4. Notice we only have one B squared since this has an open top. If this had been a cube, a closed box, I suppose would be the word for it, then we'd have 2B squared plus 4BH. So this is the thing we want to optimize, surface area. So this is the thing we need to take the derivative of. In order to take the derivative of the surface area, I want it as a function of just one variable. So I'm going to use my secondary equation to solve for H. Notice in all of these we will be using centimeters. So we solve for H by dividing both sides by B squared, and then we're going to substitute it back in to H. So we have our surface area, and I guess if you wanted to, you could write it in function form as a function of B is equal to B squared plus 4B times H, 32,000 B to the negative 2. Now, since this is an equation in terms of B, well, I'm going to simplify it before I do anything else. Surface area as a function of B is equal to B squared plus 4 times 32. Let's see, I think that's 1, 2, 8, and some zeros. I can combine those together to give me a B to the negative 1. So now I can take the derivative. The derivative of surface area as a function of B is d SA dB, or SA prime of B. So 2B minus 128,000 B to the negative 2. All right, well that can be written as 2B minus 128,000 over B squared. Getting a common denominator gives me 2B cubed minus 128,000 over B squared. Now, finding critical values, we have 2B cubed minus 128,000 equals 0, as well as B squared equals 0. So my critical value, that's looks like is going to be the winner, is B cubed equals 128 1,000 divided by 2 is 64,000. And the cube root of 64,000, and I think that's 40. Sounds like 40 to me. All right, so that's our critical value. We need to determine whether or not that gives us a maximum or a minimum of this thing. So here's 40, here's 0. Less than 0 is outside of our domain. And take a test point. How about 1? Putting it back in to our derivative equation to find this is the shape of our function in terms of b. So if we use 1, we get a negative number for the top and a positive number for the bottom, so that is decreasing. And then there's no upper limit to what b could be. If b is really flat, that means you just have a really short box. So if you pick like 100,000 or whatever, 100,000 cubed times 2 is bigger than 128,000. So you have a positive number on top, a positive number on the bottom, which gives you a positive slope, telling us that SA has a minimum when B is 40. So the questions were find the dimensions. The dimensions will be the base and the height. All we have to do now is substitute our base back in to our height equation, which we have way up at the top up here. So height is going to be 32,000 divided by 40 squared. Forty squared is 16 and some zeros. So 16 goes into 32 twice. I'm thinking that looks like maybe 20. All right, and that gives us the dimensions that optimizes, that is, minimizes the surface area.